doing page 3. So that's the material, and let's see if we can begin. So this is the start of describing what will turn out to be a two-step Markov chain. So I'll label it that way, even though we haven't talked about what a Markov chain is yet. So this is the two-step Markov chain. And we start off by saying, well, suppose we're looking at a machine that is important for some function. So you can think of it as a printer if you want. The math and stat department has a couple huge printers in their mailroom. And one of them is really the workhorse that does most of the printing for people in the department. Now, actually, what I'm describing is how it used to be, because again, so many of us are teaching from home that we're probably using our own printer, but that's okay. Let's talk about how the department functioned when we were there entirely in person. When we were entirely in person, this printer would be serving the department. It's a huge printer. And to make it simple, it either was working or it wasn't working. Now, sometimes it's not that simple. Sometimes it's not working, but it's easy to fix, like if the paper is jammed or if it needs new toner or something like that. So sometimes the fixes are really easy. But what I'm trying to describe is something even simpler than that. We're going to make an assumption that the machine is either broken or working. And by the way, it doesn't have to be a printer in the math and stat department. It could be any machine that, a company or a bunch of people are depending upon. So how are we going to label this? We're going to consider there being two states. So let me put that down. There are two states. And we'll denote the state as 0 as being broken. That means the machine is not working. And the state 1 will represent that the machine is working. And I'm thinking of this, this is the title of the talk, two-step Markov chain, and I'm thinking of some machine. Probably I'll call it a printer as we go along. Okay, so if you put the two states into a set and you call it script S, this is called the state space. So this is a very simple model. There's only two states. The machine is either working or not. Now we have to take care. We've already called capital S something. We called that the sample space. So we don't want to mix up the state space with the sample space. And I think it'll become clear as we go along. Okay, now one way to represent what's going on with this machine is to draw a picture. So let's do that. So let me see if I can move my screen a little bit. See if that works better for me. So here's a picture. We could be in state 0, or we could be in state 1. And as the machine functions or doesn't function throughout the day, you could be going from one state back and forth to another. So let's assume I'm going to use numbers. This is one difference from what I'm doing from what the book is doing. The book does this a little more abstractly, but I'm going to use numbers because I think it'll help people track the argument, at least initially. But I'll warn you, after some time, I will go to some symbolic representation of what I'm doing. So I'm going to assume that if the machine is broken, there's a probability that it'll be fixed. And the probability that it'll be fixed, I'm going to assume, is 3/4. which I'll represent as 0.75. That's a probability. And that's saying that if you're coming from the zero state, that's where this arrow is emanating from, and you're going to the working state. And what that means is the machine is being repaired. It's currently broken and it's going to be repaired. And there's a 75% chance it will happen. Why is there a probability? Well, if you've ever tried to fix something, it may not be repaired today. It may be repaired tomorrow when the people are available, or sometimes they might come out to fix it and they may not have the right piece. So there's a bunch of random things going on here that could affect whether the machine is going to be repaired or not. So I'm just summarizing them all by saying there's a 75% chance it'll be repaired today. And therefore, there would be a 25% that's not repaired. And that we will show as an arrow going from zero back to itself. Okay. Now I could write them as fractions. It doesn't matter. Okay. So if the machine is broken, this is simply saying there's a 1 in 4 chance it'll still be broken at the end of the day. And there's a 3 in 4 chance that it'll get fixed. What else could happen? Well, we could have a working machine, which is good. And if we have a working machine, let's assume there's a 90% chance it remains working. And that would mean there's a 10% chance that it breaks. Okay. So this is a simple model. There's only 2 states and there's only 2 places to go. You're either working and you're going to break or continue working, or you're broken and you're going to stay broken, or you're going to be repaired. And that's the motto we're assuming for this machine. And what's implicit? What's implicit is that we can't be sure of a repair happening in the next day. There's a certain probability of it happening and a certain probability of it not happening. Any questions thus far? Okay, well, first of all, let's see, I have my title wrong. Not a 2-step Markov chain. It should have been 2-state Markov chain. Now let me go back and fix that. And because you can see there are only 2 states. All right, now there are a bunch of random variables associated with this machine and in this model of the machine. And let's denote what they all are. So there's X naught, which is a random variable. And that represents the machine on the initial day. So the initial state of the machine. On the initial day. So if you want to think of it this way, you got the machine delivered, you take it out of the box, you plug it in, and it either works or it doesn't. And that would be the initial state or the initial day of the machine. Now, if you would rather call that day 1, you could. This is really, this 0 is not this 0. So this 0 is really time. So we're thinking of when you first start, and we started thinking of the timeline as starting at 0. Well, if X naught is the state of the machine on the initial day, or maybe the initial time you started up, what would X1 be? That would be the state during day 1 of operation. And we're pretty much assuming that during day 1, it's either working or it's not. So you could get it out of the box, plug it in, and say it doesn't start up at all, and you're disappointed. And then you call the repair people, and that's where it is on day one. Day one, it's at 0. Or it could be working as soon as you plug it in, and then so that would how this would look as well. So let me be a little clear. These are random variables. Let me talk about, well, both of them. So as a random variable, initially at time 0, so again, think of the subscript as the time. At time 0, you're either going to be at state 0 or at state 1. And so the random variable only has 2 possible values. The machine's working or not. And let's assume something about this. Let's assume the probability that x naught is equal to x. These are the values here that this takes. Let's assume, what did I assume? Let me see. I made some assumptions, but I can't find them. Oh, there they are. I'm assuming that on day 1, there's a 20% chance it doesn't start, and there's an 80% chance it does. Okay. And so what would we call these? We would call these the initial probabilities. Okay, initial again at time 0. And at time 0, you're either in state 0 or you're in state 1. 20% chance you're broken, 80% chance the thing is working from the beginning. Okay, this is a probability table. And the notation that your book uses for this, this probability he calls pi sub 0 and 0. And this one, your authors call pi sub 0 at 0. Try it again at 1. So it's a little confusing. The subscript again is the time. So when you see some subscripts here, subscripts refer to time. And why don't we talk about how time is going to look for us? We're going to assume that time is either 0 or 1 or 2 or 3, etc. So we're not going to assume that time is continuous, as it actually is. We're going to assume that we're looking at this machine initially, the first time we see it, day 1, day 2, day 3, it's going up by days. Okay, so that's how we're thinking of time. So this would be time equals 0, which is the initial time. And this is the probability. It could have used P for probability. They're going to use that for other things. So they used pi. Pi is also P in the Greek alphabet. Okay, so they using pi is a little odd because we're thinking that so much is referring to the circle, but in this context, it's referring to the probability of this system at time 0. And we're saying the probability at time 0 of being broken at state 0. So this is the state, this is the time, and the probability of being broken at state 0 is 20%. I'm just assuming that. That's not a very good thing, by the way. That's saying the product comes to you and there's a 20% chance it doesn't work. That's a little depressing. But on the other hand, there's an 80% chance it does work. Okay, so that's how those look. And then the notation, well, what about, say, at the end of day 1, if you want to think of it that way, that might be a good way to think of it. At the end of day 1, it's either working or not. And, well, we don't know what those are, but I'm going to use the same terminology. We're going to call this, and this would be the probability at day 1 of the machine either being broken or working. And the chance, this one would be called pi 1 of 0. And this one would be pi 1 of 1. So this would be what we could call the distribution, if you want, or probability table. For day 1. Okay. And the notation we'll use for all of these. Now, I only said that I only gave 2 random variables, but there are many more. Why are there many more? I just didn't write them all out. I guess I'll squeeze it in here. There's x sub n. There's the state during what? During day n. Okay. And again, n could be, I think I wrote that somewhere. Yeah, time could be any of these things. So you can think of time as being n. So this could be time 1, time 2, times 3. So in general, how would this notation look? Looks like some of it escaped me here. Be careful. Back up here, something got erased. This was 0.2 by assumption, and it was pi 0, 0. And in general, how would this notation look? It would be, if you're looking at the random variable at time n, which is really just measuring whether the machine is working or broken or working, this will be pi n sub 0, and this will be pi sub n 1. Those are the probabilities that at time n of what's going on, where x could be either of these 2 values. Okay, so the tables are very simple. And because they're a probability table, we know this column with probabilities adds up to 1. So we know that whatever pi n at 0 is, if you add it to pi n at 1, you get 1. Because the machine's either broken or working. Those are the only 2 possibilities in this game. Okay. Questions? Good place to pause for any questions. Okay. Now, well, we've already said there are these probabilities of going from broken to working and working back and so forth. Well, so we want to give names to those as well. This we call the initial probability. So that's the probability from the very starting time, 0. These are called transition probabilities. And that makes sense because you're transitioning from one state to another, or not. I mean, you could be going from 0 to itself, but that's sort of a transition as well. It's not as much of a transition as going from 0 to 1 or 1 to 0, but in one unit at a time, you could be staying where you are. Okay, so let's make that formal. Let me see. I want to do it. yeah, if we're going here, so here's our symbols for this. Suppose we're transitioning from 0 to 0. So this is supposed to convey the probability of going from state 0 back to itself in perhaps 1 unit of time, so that you can think of that during 1 day. And the probability of doing that is going to be 0.25, because you're going from 0 back to itself. So in our case, we've assigned that probability to 0.25. It could be something else. So in general, we'll give a name to this in a moment. But what we're going to say is this is the probability of a conditional probability. If at time n, you're at 0, what's the probability that at the next day, you're still at 0? Well, that means you've gone from 0 to 0, which means what? It wasn't working today, and it's not going to be working tomorrow. And that has, according to what we set up above here, a probability of 0.25. Well, now that we've done it from 0 to 0, it's sort of easy to do the other ones. The transition probability going from 0 to 1 by our picture would be 0.75. And that would be this conditional probability. If you know at time n, you're at 0, and at time n plus 1, you want to be working, that transition probability is denoted this way. So these are called transition probabilities. Okay. And OneNote keeps me honest by erasing things randomly. So it's perfect for a course on random things. Okay. Now, in general, well, there's 2 more to do. Each of these correspond to the transition arrows that we have pictured here. So we've talked about the 0.25 and the 0.75. The other 2 is going from 1 to somewhere. So if we're starting at 1, and we're next day going to be broken, so we're going from a working condition to a broken condition, the chance of that happening from what we assumed in our picture was just 0.1. So there's only a 10% of it breaking from 1 day to the next, which is good. And so that's the probability of your working today, but you're not going to be working tomorrow. Okay. And the last one to put down here would be going from 1 back to itself. And that has a 90% chance of happening. And that's the chance of, if you're working today, that you're still working tomorrow. Okay. Now, in general, for the 2-state Markov chain, these probabilities are given simpler names. So usually the 0.75 is called P. And then this would be what? 1 minus P, right? Because if you're not being repaired, then you're just still broken, right? And together, those are the only 2 things that can happen. You're getting repaired or you're staying broken. And the chance that you broke is often called Q. And so this 0.9 in general would be what? 1 minus Q. Well, be careful, Q looks like a 9. Why am I introducing these letters? Because it doesn't have to always be 75% or 10%. These numbers could change. And if they change, you have a different system, maybe a different machine, maybe a different repair service, different conditions, but it's still a two-state Markov chain. All right, a lot of terminology. Let's recap. The simple part is there's only two states. The machine's either working or not. But we're looking at it over infinite time. So we're looking at the time 0, 1, 2, 3, etc. That etc. means the time goes on forever, 4, 5, 6, etc. So two states, but the machine, we're looking at it for infinite time. The time is going up in discrete steps. It's not going up in continuous time. It's discrete time. We are going to assume an initial probability. So when we first walk into the room, what's the chance the machine is working? According to this assumption, there's an 80% chance it's working initially when you first see it, day 1 or day 0, actually. After that, there'll be different probabilities, which we don't know yet. We don't know what the probability is going to be for it to be working at day 1 or day n in general, but we have terminology for those probabilities. There's this pi notation. And the good thing is there's only 2 probabilities and they add up to 1. So if you know one, you know the other. Okay, so those are the distributions or probabilities. And those are the, what would we call these? These would be, give this a name, the probability table. Of xn, or sometimes called the distribution of xn. And again, n can be 1, 0, 1, 2, etc. And then we have these other things that are transition probabilities. The chance of going from one state to another means whether you're going to be broken and stay broken or be repaired, or going from a working machine to a broken machine. Now, by the way, we've already made a few assumptions here, and this got left off. +1. We've assumed that the probability. Let's look at one case. This is the probability of being broken today and working tomorrow. So that's the chance that it got repaired in a day's time. We're assuming that that probability is 3 out of 4, or 75%, no matter what day we're at. Okay, because I didn't say what n is. N could be 1 to 2, or we could be going from day 1 to day 2. We could be going from day 9 to day 10. And we're assuming that no matter what day we're at, the chance of it transitioning to this state from this one is always going to be this probability. So that's called being homogeneous in time. A more complicated situation would be if the probabilities vary with regard to time. And a good example of that's what's going on with the virus right now. The chance of getting caught or catching the virus 2 months ago was much less than the chance of catching the virus today, because the Delta, we all know the Delta variant is the main type of the virus that's circulating so heavily. So that shows you the chance of catching something from one day to the next may not be the same. In this model, we're assuming it's the same. It doesn't matter what day you're looking at, the chance of doing these transitions are the same. That's called being homogeneous in time. Homogeneous in time. If you're not homogeneous in time, there are Markov chains and they're more complicated. We won't be studying those. We're going to be looking at those that are homogeneous in time. Okay. What we'd like to know, it would be nice to know these guys. It would be nice to know if there's an 80% chance the machine's working initially, what's the chance it's going to be working on day 1? Okay. Or day 2, or any of the
any of these tables for different n? That's what we'd like to know. And that's the next thing we're going to talk about. Any questions? Because I'm going to flip the page. Hopefully you have a lot of this notation written down. If you don't, it's in the book on page 2 and 3, but I will be referring to it. Okay, so I'm going to flip the page because I think it's the safer way to go with this machine. And if I flip the page, I'll add a page, I'll put on some lines and keep going. So let's talk about how to find. So the first thing we want to talk about is find this table. And the probabilities that are in this table. We've already said this would be probability on day 1 of being at state 0, and the probability on day 1 of being at state 1. And we'd like to know what those are. Okay, so here's a way to do that. What is this? This is nothing more than the probability that at day 1, the machine is broken. Okay, so the natural thing to say is, well, how was the machine working from the beginning or not? So we can make a tree. This would be the state at initially. So initially, the machine's either broken or working. But broken means where it's state 0. So it's use 0 for being broken. And 1 means that it's working. And this would be the initial day. And then after that, the next day, which is what we're calling day 1, the machine's either broken or working as well. Same thing here. Okay. And let's put in, so this is a probability tree. Let's put in some of the information. What's the chance that the machine was not working when you first plugged it in? Well, that was 20%. That's what we assumed. And we also assumed that the chance that it was working was 80%. Okay. Now, from here to here, that's a conditional probability. That's the probability that it's broken, and it's still broken the next day. On day 1, it wasn't working initially, and it's not working on day 1. And in terms of our picture, well, let's keep our picture present because it's sort of important. So I'll reproduce the picture. The picture showed those transition probabilities, which are these arrows. And the chance that it goes from here to here was, I believe, 75. And this was what, 0.25? And what was the chance of it breaking? Help me. Was it only 10%, I believe? I think that's what I had on the previous page. If I'm wrong, let me know. Okay. And these are the transition probabilities. So the probability of it going from a broken state to the broken state the next day would be 0.25. Plague. No one's saying anything, so I'm probably okay. But I'm worried. So I'm going back. Yeah, that's right. I got the picture right. All right, good. Okay, but that enables us to figure the rest of the tree. So if the chance of going from here to here is 0.75, the chance of being repaired is 0.75. If you're working initially, the chance that you're still working is the 90%. And the chance that you go from a working state to a broken state is only 10%. Okay, so this tree applies. from going from initial day to day one. And what are we after? We're trying to figure out the probability on day one of being broken. Well, you're either broken and you went down this path because here you ended up being broken, or you went down this path and you're broken on day one. So we've done such a calculation before. Let's do it again. The probability that X on day one is broken, or 0, would be the chance of traveling this path, which is the 0.2 times 0.25. Plus the chance of traveling the other checked path, 0.8 times 0.1. Okay. That's similar to what we were doing last week or even Monday, by saying that we can use the tree to figure out the chance of being in a certain condition. Before, we were trying to figure out the chance on the second pick of that you got a red item, right, from a container. Now we're trying to figure out the probability that on the second day, essentially, even though it's called day one, that this machine is broken. Well, that depends where you're coming from initially. Okay, so we do the math. 2 times this is just 0.5. And this times this is 0.05, I think. And this is what? 0.08. And so together it's 0.13. So we have found this value here to be 0.13. And we can find this value in a similar way. We can go through the tree and seeing the chance of going from a day one that you're working, and that would ultimately be going down this path here or this path here. We could do it that way, but we also know that the sum of these two add up to 1. So the easier way would just be to say that this is 1 minus this, which is 0.87. Okay. So we have, from our assumptions, which were twofold. The assumptions we made, we assumed, now let's write them all down. We assumed these transition probabilities, which appear in the tree over here. And we also assumed these initial conditions. So the chance that on day 0 you were broken is only 20%, but the chance on day 0 that you were working was 80%. So we assumed all of this stuff, and we assumed everything in this picture here. It all got translated into this probability tree, and it allowed us to find out the table for X1. So what does it mean? There's a better chance that the machine is working on day 1 than it was initially, which is good. You'd like the machine to have a better chance of working than worse, okay? Any questions on this calculation? Well, okay, is it clear? Because the homework is going to be redoing this calculation for different probabilities. So if you're not clear what I'm doing, this is a good time to chime in. Let's do it again. Why would we do it again? Well, because maybe you want to know what the table looks like at day 2. Okay, so if we want to know day 2, we want to know the probability that the machine is working or not on day 2. That's the probability that on day 2, one of these values either working or not. And the notation would be what? Pi day 2 not working, pi day 2 working. So that's the notation for those probabilities. And what I would do is repeat the idea we just did. So let's do that. let's say this is day one. Give me a minute. Lost my OneNote. It's back, but I got to be share it with you, I suspect. Yes. Okay. I assume you could all see the screen again, but I've lost something in the process. Unfortunately, I lost my tree, so I'm going to draw it again. This is day one. This is day two. I'm either broken or working. The chance that I'm working on the chance that we're broken on day one, we just figured out. That's the 0.13. This time that goes here. The chance that you're working on day one is 0.87. That goes there. So this makes use of the previous calculation. For the rest of it, those are transition probabilities. Those don't change. So the chance of going from broken back to broken is still the 0.25 as it was before. So I'll put it in here. The chance you went from a broken state to a working state in 1 day's time is 0.75. You can get those from this picture. The chance from going from a working state to a broken state in 1 day's time is 10%. And the chance of going from working to working is 90%. So what you should do is compare this tree up here to this one over here. From here, we're going from initial day to day one. We had the initial distribution to be 0.2, 0.8, and these were the transition probabilities. Now, we're going just back 1 day, and we're making use of what we've already found. We already know the probability of being broken or working on day one. The transition probabilities don't change. And so we can use this tree to get what we're after. Now, somebody could ask, well, could you go all the way back to the initial day as well? Yeah, you could. The tree will be longer. It'll have 3 steps instead of 2. Would it work? Yeah, but it's more complicated than it need be. You might as well take advantage of what you've already done. And that's what I've done in this new tree. So let's figure out the probability on day 2 of being broken. That is, let's figure out this thing right here. Well, I could be broken on day 2 by either going down this path or this path. So this way, the multiplication rule would give me 0.13 times 0.25. And this way, the multiplication rule would give me 0.87 times 0.1. Now, I've got my notes in front of me. I think I can just tell you what that turns out to be. I think it all turns out to be 0.1195. You can do the arithmetic with your calculator. And what is that? That's this guy. So this works out to be 0.1195. If you do the other one, it's just 1 minus this. Let me see if I actually did that somewhere. Yeah, it's 0.8805. And again, you can get that in 2 different ways. You can find the probabilities of ending up at these places, use the multiplication rule. It's actually the multiplication rule along the path, and it's also the sum rule because you're saying you're going down this way or that way. So it's both rules. You can find it that way, or if you prefer, you can just say this number would be 1 minus this and get it that way. Okay, is it clear what I'm doing? Because if it's clear what I'm doing, you can do this to your heart's content, right? You could find the probability of the machine working 10 days after you purchase it, or a month after you purchase it. You may have to work up to it using this notation, and we'll find different ways to do that soon. But this will give you that, okay? So that's pretty nice. Any questions? Let me see what my time is leaving. Let me see what I can do in the time I have. Okay. What I did next is what the book does. The book doesn't do a numerical example. I'm leading with a numerical example because I think it'll be easier for you to follow. So now that I've got this numerical example, why don't I give you a homework problem to make sure you know what's going on here. So homework. Let's ask you to find what's the probability that the machine is still working on day 3? And how about that it's still working on day 4? So I'm asking you to do this process two more steps. Okay, that's homework. What are you assuming? You're assuming everything I'm assuming here. You're assuming, if you want, you can assume this table right here. That would be a fair assumption. And these transition probabilities, and do the same technique 2 more times to get these probabilities. By the way, notice the probabilities are getting bigger for it working. The probability that it was working on day 1 was 0.87. The probability that it's working on day 2 was 0.8805. What's a reasonable question to ask? What if this thing was going on for a long time? Like a couple months of this kind of working, broken, back and forth. And so what would be the probability after, say, 3 months, so let's say 90 days, what would be the probability if you came in 90 days after the purchase of this printer or machine? What's the chance you're going to find it working? Well, there's 2 ways to think of that. You can do this process 90 times, but that would be sort of a pain. The question is there a long-term probability that this thing stabilizes around? And the answer is yes. And we're going to find that as well. That's called the steady state. So that's answering the question, if you have a process that's random in the way that we've described, and we want to know characteristics of it after a long period of time, is there a way to do that? And in a way, that's analysis. That's what you're really asking is there a limit? Here's the limit question. Initially, there was an 80% chance that this machine was working in pi for x0. Then it went up to 87. Now it's gone up to 8805. Is there a limit? Is this thing converging to a numerical limit? Okay, and this is an example where when you're talking about limits, you're talking about analysis, where analysis or calculus, either way, starts to merge with probability. Okay, let me see if I can, in the few minutes I have, redo all of this. So I'd like to redo all of it, but this time I'll make a different assumption. So let's redo this more generally. Redo this problem more generally. Well, what does that mean? The initial transition probabilities are the same. There's an arrow going up, there's an arrow going down. There are two loops. But instead of giving you numerical values, I'll call this one P. I'll call this one Q. P and Q are probabilities, so think of those as numbers between 0 and 1. Could they be 0? Yeah, well, it could be, but then you won't have the transition at all. So probably better think of as what? Think of P and Q as being strictly between 1 and 0. What are these loops? Well, if the chance of going up is P, the chance of staying still would be 1 minus P, only two options. The chance of going down is Q, the chance of staying still here would be what? 1 minus Q. Okay, so replace the numerical example, which is up here, by a more general example that looks like that. And then what else would we have to know? Well, instead of knowing the transition probabilities, well, I guess these are the transition probabilities, but instead of knowing the initial probability, give those numbers too. So the initial distribution for time 0, or day 0, we already have symbols for that. This thing is pi 0, 0. And this thing is pi 0, 1, right? Okay, so now redo this whole problem, replacing this. And before this was 0.2 and 0.8, right? But now just column these things. Before this was 0.75 and this was I forgot already, 0.1. But now column P and Q. So if you redo this whole thing in general, what would X1 turn out to be? So redo it in general. I know I'm almost out of time here. If I want X1, it's still just taking two values. It turns out that this one and this one here is what we're calling, this is the probability that X1 is equal to little x. And in this case, we called it pi at time day 1 of 0. It works out that this is equal to 1 minus P minus Q times the probability that X equals 0 plus Q. Okay. So I'm saying if you did this whole problem using the general terminology that I've got here, this thing turns out to be this. From that, it's not hard to get this, right? Because this would just be 1 minus this, right? So if you already have this expression for that, you can just subtract it from 1 to get the expression for that. I was going to do this if I had more time, but I don't, so I'm leaving it for you. That's homework. So there's a second homework problem now. This is homework problem 2. I've already given you one earlier. By the way, how do you do it? The same way we just did the numerical example. But if you get, flummoxed by it, I guess, it's in the book. So read page 2 and 3, and they'll show you how to get this as well. And then I'm going to get greedy, do it for X2 as well. So X2 would be 0 and 1. This guy would be pi 2, 0. Find the expression for that. Can I be a little nicer? Maybe. Let me see if I can be a little nicer. I can give you an expression for it, so you'll know when you're getting the right answer. It works out to be 1 minus p minus q squared times the probability that x0 is 0. Sorry about that. Plus q times 1 minus p minus q plus q. Show this. Show that pi2 of 0 works out to be this. And if you get stuck, it's in the book. Well, it's in the book, sort of. They don't do all the algebra. They sort of just tell you the answer is this, and then they expect you to be able to figure out how to get there. Both of these, I think you should be able to do sort of imitating the numerical example that we just did in class. If you need help, hang around. That's what office hours are about. So I'm done with class. I'll take my usual 15-second water break here. I've given you a couple problems to look at. It would be good if you could read this stuff in the book. So let me make a reading assignment as well. I think I've already told you to read this, but it goes on. Yeah. So read 2 through 4 from the book. Okay, I'll see you in about 15 seconds. And if I don't, I'll see you Friday.
All right, thank you, Professor.
Okay. Any questions on anything I said in class? Want me to go back over any of the slides? This is a good time because they're all pretty much at my fingertips. So if anyone has any questions about any of the example or any of the assumptions, this is a good time to ask.
I have a question
Please.
about the example, the previous one. The 0.2 and the 0.8 you just made up, right? They didn't come from anywhere.
That's correct.
Those-
Well,
okay.
Okay.
As long as they add up to 1, right?
Yeah. The truth is, what you're saying is correct. I made them up. And just so we can get started. And I picked something that I thought was halfway reasonable. So, I mean, I could, yeah, they have to be probabilities. They have to add up to 1. That part is for sure. Could I have reversed the probabilities? Could I have called P0, 0.8 and the other one 0.2? Yes, I could have. But that would have been a rather pessimistic product, right? Because that would tell you there's an 80% chance your product doesn't work from the get-go. So the reality is the company, whoever makes this product, they probably know the statistics on how often it works from day 0, right? Or from the initial day. So yeah, I made it up because I have a fictitious product here. I don't know the product personally. But in reality, whoever produces such a product probably has tested it enough or has experience with it. So they probably have some idea what that initial probability should be. So it's not all, what I'm trying to say is, I made it up for convenience, but in reality, if you were working this problem for a company, they probably would have the statistics.
Okay, so if this were on a test, you would give it to us as given.
Yeah, if it were, if you're worried about or concerned about how this would appear on a test, I would give you those things. I'd have to. So the two circled things here are what you need to do this. You need the initial probabilities and you need these transition probabilities. So there's two types of probabilities that you need in order to make this work. If you don't have those things, then you really can't do the problem, okay? So yeah, they'd have to be provided.
Okay.
Good question. Anyone else have something? Now we can get to the homework. And I plan to do that if no one has any other questions, but if you have any other questions about, how I did something or just like the one that was just asked, what do we know? What do we, what don't we know? Those are always good questions. Okay. Well, I've given you a couple homework problems. Which one do you want me to play with? I assume you may want one of them. I'm happy to do either of them. I think the more general one may be the harder one, which is the second one, but I'll let you request. What do you want to see? Okay. You have to say something or we can't roll.
Okay.
Oh, sorry.
Oh, go ahead. Go ahead.
I would say we can talk about the second one, please.
All right, sure. Let's talk about the second one. So the second one is what I didn't have as much time to talk about. It really was all summarized in this little part here. So the first one, which was numerical, I went through fairly carefully, slowly. And then I said, let's call the transition probabilities P and Q in this way. And let's just assume the initial distribution is given in terms of these, but we don't have them as numerical examples. And then the first thing I said is if you redo what we did, this should be the answer for X1. And if you did it up to X2, you should get this. So why don't we do those? Why don't we just, and that's what this homework second problem is to confirm that if you use the process that I just went through, that pi1 of 0, which is the chance after 1 day of the machine being broken, would be this. And then, of course, this would just be 1 minus that. So let's go through that reasoning. So I'm going to switch pages because I've got maybe enough stuff on this page. So let me switch pages and do it. So add a page. Let me see if I can put some lines on this thing. So many toolbars. And it's not letting me do it, so I'm not going to worry about it. I'm just going to go to the big page. Now let's see if it lets me do it. Yes. Okay. All right, so what are we assuming? We're assuming that we have just these two states as before, that the chance of going from here to here is P. The chance of going from here to here is Q. These are the transition probabilities. So they're no longer numerical. The probability of going from here to here is 1 minus Q. The probability of going from here back to itself is 1 minus P. So that's what we're assuming. And we're also assuming that the initial distribution on the initial day has probabilities that are given like this. So now we have, this is called the initial distribution, and we're assuming that these are known, and we're assuming that the P's and Q's are known. Okay. What is it we want? We want how things look at day one. We know where either broken or working. This one would be, according to our notation, day one, the machine's broken. Day one, the machine's working. We want these. Okay, so let's go for this one in particular, because we can get this one, then it's just one minus to get the other one, right? So what was the idea? The idea from what we did before is if you're trying to see things at day one, go back one day. So we're trying to see things at day one. So let's go back to day 0. We know that you're either broken or working. And you're either broken or working later. And the probabilities are what? The probabilities that you're broken on day 0 would be this guy, which is known, assumed, I00. That's that probability. The probability that you're working on day 0 would be pi01. These things. That's maybe the going from 0 to 0 in this scheme is 1 minus p. Why? Because that's that loop. Going from 0 to 1 is p. Going from 1 to 0 is q. Going from 1 to 1 is 1 minus q. Okay. The chance on day 1 that you're broken would be the chance of ending up at either of these two destinations. So what we can say, and by the way, this is the same idea we did before. We just don't have numbers this time. We have letters. Okay. So the probability on day 1 of being broken would be, you could be broken by going down this first path. So that would be pi 0, 0 times what? 1 minus p. That's the chance of going down this path by the multiplication rule. Or you can be broken on day 1 by going down this path. Or means add. That's the sum rule. And this would be pi 0, 1 times q. Okay. Yeah. So in a sense, we're done. We have this one, but actually what I gave is an answer. Let me see if I can see what it is. I gave it all in terms of just pi 0. So we put it all in terms of pi 0. Then this could be written as what? Pi 0, 0, 1 minus p, plus this is what? 1 minus pi 0, 0. Q. Because again, what happens, I didn't write it, but it's over here. On the initial day, there are 2 possibilities and there are 2 probabilities. And they add up to 1. So this one is really 1 minus that one. And that's all I did here. And from here, you can start cleaning up the algebra a little bit. How so? Well, there's this times 1, there's this times this, and then there's this times this. So if you write it all out, this times this is pi 0, 0. This times this is minus p pi 0, 0. Q times 1 is just q. And this times this is minus q pi 0, 0. And if you combine these three terms, because they all have a common factor of pi 0, 0, what you would get is, you can factor out the pi 0, 0. You would get 1 from here, you would get minus p from here, you get minus q from here. And then the only thing left over was this term. So this would be what I think I gave you in class. Sure, that's it. Yeah. So that's telling you this is considered done. Why? Because we're assuming that the P's and Q's are known. And we're assuming, okay, so let me circle what we're assuming. We're assuming all of this stuff at the top. Let me see if I can get rid of the picture a little bit. Yeah. So we get to assume this picture and this table are all known. So everything now is in terms of P's and Q's and the initial distribution here, which is this. And so everything is this. Okay, which means if we wanted to put in the numbers from what we had in class, we should get the same answer, right? So what we did in class, just to reinforce this, P was what? 0.75, I believe. Q was 0.2, I think. Maybe 0.1. I forgot what it was. Sorry. Let me look at my notes. Yeah, it was 0.1. So in class, and the numerical example I did in class, P was 0.75 and Q was 0.1. So you can put that in for P and Q. And as far as this was like what, 20%, I believe. Make sure I got that somewhere. Yeah, I assumed that this was 20% and that made this 80%. So you could put in 0.2 for this, put in 0.75 for this, and 0.1 for this, and it should agree with what we came up with in class. Okay. And then to find the other one, to find pi 0, to find pi 1, 1, all you would have to do is take 1 minus this stuff. Okay, and you can leave it like that if you like, because everything is in terms of what you know. Or if you prefer, you could write it as 1 minus Q minus P 0, 0, 1 minus P minus Q. Okay, so that was part of the homework I asked you to do. And then I think I asked you to do the next step for pi 2, right? So why don't we do that? Any questions about this part? I don't know about you guys. I'm warming up a little bit. This feels a little hotter than yesterday. Give me a second here. Okay. So now, let's see if we can do the same thing for pi 2, 0. Find a general expression. For pi 2, 0. Okay, and pi 2, 0 is where? Pi 2, 0 occurs in this table. If you're looking at where you are on day 2, you're either broken or you're working. And the probability of being broken is pi 2, 0. Probability of being working is this. And we're in the column that it's 2 is taking different values. So we're looking for the same, we're looking for the chance on day 2 that the machine is broken. All right. Well, we would do the same thing we did before up here. Let's make the tree. Here's where we are on day 1. On day 2, we're over here somewhere. On day 2, you're either broken or working in each of these places. Okay. The easy part, or maybe the easier part, is the transition probabilities, the chance of going from 0 to 0 is 1 minus p. I can put that in here. The chance of going from 0 to 1, according to the picture, is p. It's the arrow going that way. The chance of going from 1 to 0, and that's a transition probability, that's q. The chance of going from 1 to 1 is 1 minus q. So that part of the tree we can figure out from what we're given. The chance on day 1 of being broken is what we just figured out. Day 1 being broken is that. And on day 1, working would be that. So that's how the tree looks. And if you're trying to figure out on day 2 of being broken, then you're either going down this path or this path. How do I know that? Because you got a 0 there on day 2. So there's 2 ways to be broken on day 2. You're either broken the previous day and you're still broken, or the previous day you were working and now you're broken. You just broke during the last day. So those are the 2 possibilities that have to be considered in cases. Okay, so the answer should be, from what we've sort of done before, it should be pi 2, 0 should be pi 1, 0 which is the first leg of this tree, times the 1 minus p. Or, which means add, it's a sum rule, pi 1, 1 times q. Everyone see that from this? I'm going down either the top road or this 3rd road, and I multiply along the way and then add the contributions. Okay, so that's that, except we'd like it all to be in terms of like this one. We'd like it to be in terms of the initial distribution and the P's and Q's. So we can do that, but it's going to take a little more algebra, that's all. So before I enter the algebra, the key idea is really this, which we actually covered in class. Everyone cool with the idea? All right. So then for pi 1, 0, substitute in this mess. Okay. So let's do that. It's pi 0, 0 times all of this, 1 minus p minus q plus q. Okay, so I'm using this box formula, and then I need to take all of that and multiply it all by 1 minus p. Let's see if I'm doing that right. I think so. And then I need to, well, pi 1, 1, we also did that. It was over here. Hopefully it's correct. I think it is. Yeah. So put in what pi 1, 1 is. It's 1 minus q minus pi 0, 0. 1 minus p minus q. That's this times what? Times 1 minus p minus q. Okay, so in theory, we're done. We've figured out, so what were we trying to get? We're trying to get the probability on day 2 of being broken in terms of either the transition probabilities, which are these p's and q's, or the initial distribution, which is pi 0. And we have it all in terms of that stuff. But the thing we should do is see if we can simplify it and write it in a nicer form. And I think we should be able to do that, I think. So let me look at it a little bit. Well, I actually gave you the answer. But since I gave you the answer, you might try to get into that form. Let's see. I can use that myself. Let's see. Yeah, okay. So there's a nice form of this where let's just look at what gets multiplied by pi 0. Okay, so here there's a pi 0. Hang on a second, I'm trying to figure out the nicest way to do this.
Professor, I have a question.
Yeah, sure.
For the far right side, why is it 1 minus p minus q? Shouldn't it just be times q or
Oh, this here?
yeah?
I think you may be right. Let me see what I did. I think
We're just substituting pi 1 of 1, right? And then we should still just be multiplying by q, or are we substituting q for something else? Or am I
no,
missing something?
hang on. It's just this. So pi 1, I should have lifted this, which I did correctly. But then I just didn't make a mistake. So thank you.
Okay, sorry, thank you.
Yeah, so let me just correct it. Well, actually, that's interesting. Did I make a mistake? I'll correct it, but then I gotta check again. So because let me make sure. The answer I've written down in my notes doesn't look like what I'm getting here. So let me see if I did this right. Okay, so make sure I substituted in what I meant to. Yeah, I think it's all fine. let me look at the algebra and then we'll go further. Well, I don't quite see it, but I'll play with it. So let's play with it a little bit. If I multiply everything in here by one, I'm trying to decide if I want how I want to do this algebraically. So give me a second. Let me think what I want to do. Yeah, let's just play with the terms that have pi 0, 0. So where would that come? So it looks like in this one I'd have pi 0, 0, 1 minus p minus q. And if I just multiply this by that, I'll have what? 1 minus p. So I'm just going to expand it out. Maybe there's a more clever way to go, but this will work, I think. So I'm just distributing this and multiplying this by this. And then this times this will just give me what? Q times 1 minus p. Plus, you have the same business here. I have 1 minus q. And I'll multiply that by q. And then this part, minus pi 0, 0, 1 minus p minus q times q. So all I've done here is distribute the 1 minus p through both of these terms. And I distributed the q with these two grouped as one and then this. Okay. And now what I want to do with that is try to combine these two. Because those are where the pi zeros are happening. So if I combine those two, what would we get? Well, they each have a pi 0, 0, so factor that out. And what's left is, well, they both have a 1 minus p minus q, right? So they both have that, 1 minus p minus q. We'll factor that out of both. But then I'm doing what I just did. I'm smiling. But okay, but it's okay because now what's left here is a 1 minus p. And what's left here, when you factor all this stuff out, is a minus q, right? All right, so if I combine the two underlying terms here, I really have pi 0, 0 times 1 minus p minus q squared, right? Yes, this is the same as that. And then what's left, well, I don't know what's left. Let's look at what's left. Are just these two terms. But they have a q in common, so I can factor out the q. And what's left is 1 minus p. Well, be careful. Factor out the q. 1 minus p is left here, and then what? 1 minus q is left in the other one. I guess I don't need this other parentheses, sorry. Okay, so let me see if I need one parentheses now, okay. I'm factoring out the q is common, and that leaves me 1 minus p, which is fine, and leaves me another 1 minus q, which is fine. Okay, so now if we do all that, we have something that looks like what? Pi 0, 0. And let's simplify this to be 1 minus p minus q squared. And this thing here looks like q. And what's inside? Well, I guess it would be 2 minus p minus q. Okay, that's not what I think I gave you before in class, but let me check and see. But I don't see anything immediately wrong with it. Okay, what I think I gave you in class is this, and I think it's the same. Yeah, okay, so what I think I gave you in class is pretty much the same. It looks like I00. This part is identical. But this part, if you just look at the 1 minus P minus Q, you could, if you prefer to write it this way, could write it as Q times 1 minus P minus Q. 1 minus P plus Q. So you could write this term this way, and I think that's what I gave you in class. They're both the same. Okay, so this is the second part of that problem. You could either stop here at pi 2, 0 is equal to this, or stop here. They're both the same. So the probability of being broken on day 2 is all written in terms of the P's and the Q's, which are the transition probabilities, and the initial probability of being broken on the initial day. And that usually would be given to you. Now, if you want to finish the rest of it, if you wanted to find out pi 2, 1, it would just be pi 2, 1. It would just be 1 minus pi 2, 0. And for pi 2, 0, you can put in either of these and get an expression. Now, the one that the book is interested in is this one. So let's touch base. Well, okay, before I touch base with the book, any question on the calculation? It's mainly algebra. Well, I mean, after you have the tree, the probability stuff is here. So we've already figured out this one from that, and now we're going for pi 2, 0, and we're using the tree to get this, and we substituted both of these into here, and the rest is algebra. I hope you could appreciate why I did the numbers first, because if you do this all with P's and Q's, you're just sort of lost in a maze of algebra. Now, any questions before I go back to the book? I was going to make a point. Okay, so question?
Oh, no, I was just gonna say no questions from me.
Okay, good. So let me go back and see if I can make a point. This on page 3. On page 3, they do the same calculation. And they more or less leave it like, let me see how they leave it. Okay, they leave it like this way, but they write it one slightly different way. So they write this as pi 0, 0, 1 minus P minus Q squared. And then the rest of it, they write, well, they actually go back to this, you can think of it as Q times 1 plus 1 minus P minus Q. And that's the same as this. And they write it that way. Now, the reason they write it this way is they see a pattern. So let's make this point, because this is sort of where things get interesting. Let's box this guy. And they're ready to make a leap of generality. Their leap of generality is, well, look, we've already found pi 0, 0 to look like this. And we just found pi 2, 0, 0 to look like this box formula. And now what they're going to say in general, let me put it in here, in general, that they can find pi, so I should use their notation. I think they use n, but let me double check. Yeah, they use n, great. That n, pi n0 looks like in general this expression. And it's expression 2 on page 3. The 1 minus p minus q to the nth, 1 minus p minus q to the nth times the summation oh no summation times pi 0, 0 plus q. Here comes the summation. The summation from j equals 0 to n minus 1 of an expression that looks like 1 minus p minus q to the j. And that's equation 2. What do they call this? Equation 2 on page 3. Okay. Now, that's a jump, but let's at least see that it sort of agrees with what we have. So when n is 1, it would just give us 1 minus p minus q to the first times pi 0, 0, which is pi 0, 0, 1 minus p minus q to the first. It gives us this first term. And then the summation, when n is 1, then we've got a summation going from 0 to 0. So we only get the 0th term of this, but this expression to the 0th is 1, and you just get q. So that general expression agrees with this when n is 1. Now let's check and see that this general expression agrees with this when n is 2. When n is 2, you have 1 minus p minus q to the second power times pi 0, 0. That's the first term here. And when n is 2, then there's two things to sum here, because you're going from 0 to 1 this time. When j is 0, you get all of this to the 0, which is just 1. So that's giving you the q, which is right here. And when when j is 1, then you get another 1 minus p minus q to the first power times q, which is this term. Okay, so I circled this one, but the one I wrote down here, if you actually expand out the sum, is what they're doing. But since this equals this, these are all the same. Okay, so what's the story? This formula agrees with the two that we have. So they saw a pattern. They saw a pattern how this would progress in general. And the pattern is basically, let me see if I can summarize the pattern. The pattern is this term you'll always keep, pi 0, 0, and it's always going to be 1 minus p minus q to the nth power. N is where n is the day you're at. Here it's day 2. Up here it was day 1. So you're always going to have a term that looks like that. And then they're saying that, let's stare at it a little more. they're saying that basically the rest of the expression we want is the sum of this kind of thing, which by the way is a geometric series. And let me see. So basically all you're really doing is multiplying. So if you wanted 3, what is this thing predicting? It's predicting that pi 30 would be 1 minus p minus q to the third times pi 0. And then it's saying that basically take what you had for 2. So all you've done here is multiply everything through by 1 minus p minus q, I think. Let me make sure that's true. So if you just multiply everything through by 1 minus p minus q, this becomes this. This becomes q times 1 minus p minus q squared. And this becomes what? Just that, q 1 minus p minus q is, well, this is clearly that. Is this the sum you would get here? Well, let's see. When j is 0, oh, and then you have a plus q. You have to tack on a plus q evidently. And when j is 1, then you get this guy, and when j is 2, you get that guy. So they're suggesting that the first term goes up in a simple way, just multiply by 1 minus p minus q. Multiply everything in what you had after that by 1 minus p minus q, and then add a q. And if you do that, you get this sum. Now, that's a very nice relationship. If you're into the math, you might want to actually prove it. I'm not that much into the math to do it, but it wouldn't be hard because it would be a proof by induction, right? You would assume this formula holds for n, and then try to show that you get the same result for n plus 1. And you already know how to get the result because the result for n plus 1, we've already been doing that. How do you get from day n to day n plus 1? You use this probability tree and go through the calculation. So that's how the proof by induction would work. So if you're into the math and want to actually try to prove this by induction, have fun. Or I'll even do it with you if you really want to sometime. But that's a way to think of this. So this is cool. Why is this so cool? It's cool because it's telling you the chance of the machine being broken on any day in terms of what it is on the initial day and what the transitions are. P's and Q's are the transition probabilities. And what it can do, what can it do for you? The next thing that we'll probably do, I'll do it in class next time, is to take the limit of this as n gets large. Because that'll get you what I mentioned in class a little earlier, the steady state probabilities. And how that works is pretty cool because this is a geometric series. So you might want to review what do you know about the sum of the geometric series. I don't want to do much more because I'm really covering what I will be doing next time we meet. But if you read this page 3, you'll be seeing it. I don't think I'm going to prove this by induction, this formula, but I am going to use it. So that's something you might want to think about. Questions on anything I've been saying? I think I've done your homework. Well, at least the recent stuff. I didn't do the numerical examples. Those I'll leave for you. How are we doing? Is this alphabet soup? Too many letters? Are you okay with it?
I'm gonna mess around with it on my own.
Yeah, no, that's the only way to really, you got to make it your own, right? You could only, math is not a spectator sport, right? You got to get in and do it yourself, definitely. So I agree with that. But hopefully I've given you some of the ideas on how it works.
Yeah, for sure.
Any questions? Let me see who's still with me here. I've got a nice group still with. Like a group of 6 or 7. I think I'm ready to stop unless I'll hang around for anyone who has maybe either math or, advising kind of questions for a few minutes. If you have any of those kind of questions. And it might be some of the people who were thinking about adding the other class. Maybe you want to talk about that or not. It's up to you. And for the rest of you, I'll see you Wednesday.
Thank you, Professor.
Yeah, have a good one. So,
Next, see you Wednesday.
sounds good. Anyone that I can help in an advising sort of way? Or anyone on the trying to figure out whether to add or to subtract a class? You're good?
Yeah, Professor, I think we're good for now. I'm gonna head out.
You're good, then I'm gone. I'll see you Wednesday.
See you Friday. Thank you.
Yeah. Oh, sorry.
Oh, actually, I'll see you later, actually.
Oh, I think the people who wanted, I still have the same undergrads who wanted to be on the mailing list for the other class. So if you're still interested, feel free to come. If you're no longer interested, that's cool too. Right.
All right.
See you Friday.
Bye-bye.
Take care.